Let's talk about one of the most common gadgets in your house, the thermometer. It seems so simple, right? But it's hiding a pretty profound scientific secret, a fundamental rule of the universe that makes it possible to even ask the question, what's the temperature? Really think about it for a second. You stick it under your tongue or in a Thanksgiving turkey, and a little while later, it just gives you a number. But how? How does that simple little tube of mercury or a tiny digital sensor actually know the temperature of something else? It's a question we almost never ask, but the answer is just fascinating. So, to crack this little mystery, we first have to get our heads around a key concept. It's called thermal equilibrium. And you can think of it as a state of, agreement. You know how it works. You put a hot mug of coffee on a cool table. Heat flows from the mug to the table. But it doesn't do that forever, right? Eventually, they kind of settle down, the flow of heat stops, and they arrive at the exact same temperature. That steady state, right there, that's what we call thermal equilibrium. A great way to think about it is like a temperature handshake. When the two objects first meet, there's this exchange going on. But once they've agreed on the terms, the temperature, the handshake is complete. No more exchange. They're totally in sync. Okay, so this whole equilibrium thing, it's absolutely crucial because it's all governed by an incredibly elegant, super simple rule. A rule so fundamental that it's the entire reason your thermometer works at all. All right, let's break this down logically. Imagine we have object A, let's say that's you, and you're in thermal equilibrium with object B. They've done their temperature handshake. They're at the same temp. Now stay with me. Let's say that same object B is also in thermal equilibrium with a third object, object C. So B has shaken hands with A, and it's also shaken hands with C. And here's the magic. Logic tells us that A and C must be at the same temperature. They don't ever need to meet or touch. B has acted as the go-between, confirming they're both exactly the same. And that right there has a name. It's the Zeroth law of thermodynamics. It's this simple but incredibly powerful rule that says, hey, we can use a third object to reliably compare the temperatures of two other objects. It's basically the law of the temperature middleman. So now we can finally connect this kind of abstract law right back to that thermometer sitting in your medicine cabinet. You see, the thermometer is our object B. It's that reliable go-between. It's the trusted agent we send in to do that temperature handshake for us. So here's how it plays out in the real world. Step 1. The thermometer, our object B, touches you, object A. They hang out for a minute and reach equilibrium. Step 2. That same thermometer has already been calibrated against some known standard, maybe the freezing and boiling points of water. We'll call that known scale object C. So because of the Zeroth law, we now know that you, object A, are at the same temperature as that marking on the scale, object C. And just like that, the mystery is solved. And what's really, really cool about this is that the law doesn't care how the thermometer works, seriously. As long as some physical property changes consistently with temperature, any property, we can build a thermometer with it. This one single law just throws the doors wide open for all kinds of ways to measure temperature. And this is the law in action. Right here. A classic mercury thermometer, it uses the changing length of the mercury. A modern digital one, it's using electrical resistance, which changes predictably with heat. Even super precise lab thermometers might use the changing pressure or volume of a gas. They all look totally different, but they're all just a reliable middleman, our object B, and they all work because of the Zeroth law. Okay, so there's probably one last question nagging you. Why the weird name, Zeroth law? Shouldn't it have been called the first law? Well, it's actually kind of funny. It's because it was a total afterthought. The first and second laws, the ones dealing with energy and entropy, they were figured out way back in the 1800s. But it wasn't until the 1930s that scientists had this aha moment and realized they'd been assuming something even more basic all along without ever actually writing it down as a law. They couldn't just call it the third law because, logically, it came before the others. You have to be able to define and measure temperature before you can even start talking about heat energy. So, in a really clever bit of naming, they just stuck it before number 1. They called it Law Zero, the true foundation, the bedrock that all of thermodynamics is built on. So the next time you check the temperature, just take a second to remember that elegant, simple bit of logic that makes it all possible. The zeroth law was hiding in plain sight this whole time. Which kind of makes you wonder, right? What other obvious laws are secretly running our world, just waiting for us to notice?